Welcome to the next instalment of National 5 Physics. Today we're going to be talking about projectile motion. Okay, now the key concept that we need to understand for projectile motion is that every object that falls to the ground falls at the same rate. And this was a concept coming up that was brought up by Galileo, so years and years ago. But if you go on YouTube, there's a couple of really good videos that you can watch that prove this. One of them is Brian Cox. He drops a bowling ball and a feather in a room where they've sucked out all the air, and another one is an actual video from the space mission to the moon where they drop a hammer and a feather together and show that they both land on the ground at the same time. So those are two videos you can have a look at that will prove that. And if you believe that if you understand that two things which are dropped will land at the ground at the same time regardless, then what you can see is that if you ping something forward and drop something at the same time, they will both fall to the ground at the same rate. And so if we were able to take snapshot pictures of it as it went down, you would end up with something that looks like this, seeing both of those falling together. So each of these will be in line with each other because they're both falling at the same rate, even though one has been dropped and one has been fired. Okay, so this is our dropped here, and this is our fired. Okay, and so you end up with something where everything falls at the same rate. Okay, now in projectile motion, what we're going to be doing is we're going to be looking at this to calculate different aspects of this. So for example, this distance that has travelled is the range. We're going to be calculating things like the range, the height it's fallen, the final speed as it hits the ground, things like that. So I'm going to take you through an example, and hopefully by the end of it you'll be good enough to have a shot of a few questions yourself. So our key definitions, okay, of projectile motion is that the horizontal motion, the object moves at a constant speed horizontally. So all objects that are fired horizontally move at a constant speed. And all objects that are dropped are going to accelerate towards the ground at the rate of gravity. Okay, so for us, that value of acceleration towards the ground due to gravity is 9.8 meters per second squared. Okay, and that's going to come in extremely important when you're doing these questions, because you need to know that. So anything that falls to the ground that accelerates towards the ground at 9.8 meters per second squared. Okay, now we've learned a couple of equations, and now we're going to separate them out. So our horizontal and our vertical are going to be analysed separately as we do these questions, and so we're going to keep the equations for the vertical and the equations for the horizontal separate, because the equation for the vertical is A equals V minus U over T, because V varies depending on the acceleration. Okay, so it's not a constant velocity. But with the horizontal, there's no acceleration taken into account, so the velocity is constant, and you can use that equation. Okay, what we're going to do when we're solving these questions is we're going to set up what I call a t-table. Okay, and so if we set it up as a t-table, we'll have vertical on one side and horizontal on the other. Okay, and in the vertical you'll have an initial speed and a final speed, because it's speeding up, or it's speeding up towards the ground. You'll have an acceleration, so you get to have all of these written down, and you'll have time. But in the horizontal, you'll only have the horizontal speed, the distance it travels horizontally, which is the range, and the time. Okay, and then the key point here is that because they all fall to the ground at the same rate, the time is the same in both columns. Okay, the time is the same in both columns. Now we're going to use this, and we're going to give this worked example a shot. So we've got a stone thrown horizontally from the top of a cliff at 25 meters per second. So first thing I'm going to do is I'm going to sketch a wee cliff, and we've got a stone being thrown horizontally at 25 meters per second. Okay, and for part A, we have to calculate the height of the cliff. Okay, so it's going to take 8 seconds and it's going to fall down and land somewhere over here, and we have to calculate the height of this cliff. Now, if we set up our t-table, the height of the cliff is not on the t-table. Okay, all we have u, v, a, t. There's no height on that side, so we can't use any of these to calculate the height. So we're going to have to work out these things and then try and find out the height. Okay, and in the horizontal side we have v, d, and t. The only thing we can do now, is we can start to put in the things we know. Okay, and now if it's fired off of the cliff at 25 meters per second, that's its horizontal speed. So we can put that in there on that side. Now it's specifically on that side because it doesn't affect anything on the vertical side, it only affects the horizontal side. Okay, but the 8 seconds in the question, time is the only thing that's the same on both. So the 8 seconds fills in there quite nicely. Now, if it's fired horizontally off a cliff or thrown horizontally off a cliff, it'll have an initial vertical velocity of 0 because it will not have started falling yet and it will not accelerated towards the ground. So it's going to start with an initial vertical velocity of 0 and it's going to have an acceleration of 9.8 meters per second squared towards the ground. And so for part A, what we need to do is we need to work out the vertical velocity. So we're going to use our equation for acceleration, which is a equals v minus u over t. We're going to put in our numbers, and so it's going to be 9.8 is equal to v take away 0 divided by 8. So v is going to equal 9.8 times 8, okay? And what we're going to do is, once we've got this answer, which is 78.4, we can put that into our table, okay? And I've gone and wrote the other things out, but we'll get there. Okay, and so we've got 78.4 going in there. Now, I'm going to have to move on to the next page to use this because I've run out of space, but in order to get the height, you know the initial speed, the final speed, and the time it took to get there. So you need to work out the displacement travelled with all of those pieces of information. So what we can do is we can draw a quick graph. Okay, now a velocity time graph has time along the bottom and velocity up the side. Starts from 0, and if I say that that's 8 seconds there, so a terrible 8, let's try that again, 8 seconds there, and the maximum speed it gets to is 78.4, this area in here that I've shaded and highlighted, that area is equal to the height of the cliff. So in this case we've got a triangle. The area of a triangle is a half times base times height. Okay, and so with our half times base times height, we're going to have a half times 8 times 78.4, which comes out as 313.6 meters. Okay, so our cliff is 313.6 meters tall. Okay, so if we go back to look at the question, we've worked out the height of our cliff. Okay, the only other thing is work out how far from the foot of the cliff does the stone land. So now we've got to work out this distance here, which is also known as the range. Okay, but that is the horizontal distance travelled, which is that in there. Okay, so what we can do now for part B is just use speed, distance, time. So the distance travelled is equal to speed times time, so it's going to be 25 times 8, so 200 meters. Okay, I hope that's helpful. I hope you have a good grasp on this now and are able to get through the questions this week. Don't forget to subscribe to the page and give this video a like.